Yeah, welcome back. So now let's get down to a little bit more modeling stuff. As I said yesterday, yesterday was like setting up like what the multi-element task is and what kind of decision-making learning tasks would be relevant as a good starting point. But today we're gonna in this morning session we're gonna talk about introduction of the reinforcement learning model, quite very simplest version of reinforcement learning model, and then we're gonna introduce how we can use this reinforcement learning model to analyze the behavior data. So like we are talking about maximal likelihood method to estimate the model parameters, and then afterwards we're gonna talk about how we can extend this basic reinforcement learning models to social learning strategies or social interaction, what we are interested in. All right, so yeah, so this is kind of abstract diagram of reinforcement learning model. So as you see here, so there are two components, like environment, which we talked about yesterday. Like we set up the environment as a two-armed bandit or multi-armed bandit program. But what we need is still need is an agent, right? So we need an agent algorithm, how they should behave under this environment. So then agent and environment is connected somehow, and then so this is like a kind of two functions, right? So environment is a kind of function where the action is an input, and then some output comes out, like the reward, or sometimes environment change its own state as a reaction. So these are output, and then given these output, agent these output are going to be an input for the agent. Then the agent then produce some next action as an output. So agent is also a function. So agent function, right? Let me introduce this naive farming guy again, right? So he's again he's still very naive, so he doesn't know what to do, right? So he's a poor guy, but he's now trying to do either potato, wheat, plant, as as we talked yesterday. Right. So yesterday we just talk about I just sketched this guy's behavior, and then we played a multi-armed bandit program together. But let's get down to what would happen inside inside his brain or inside of his mind in this reinforcement learning task. So let's say at the beginning, that's the very first season, he doesn't know which one is better. So inside of his his brain, his mind, he just have a more or less equal preference over potato and wheat. All right. So then, but let's say he just happened to choose the potato for the first plant season. So he tried potato, and then afterwards he get a kind of a reward, and then let's say it's a poor yield turned out, so unlucky. And then so this reward experience then goes to the feedback to his next belief. So he now knows potato might be worse option than wheat. So now his belief is updated. So then based on this belief, then let's say now next season he choose wheat instead, and then it's turned out it's better rewards than previous one, and then all right, then wheat seems good. So then this new experience and further feedback to his own belief, right? Then this belief then it further produce the next choice. So this is like a belief update or learning and the decision making, this recursive process. What is interesting, or what is utility of using this kind of reinforcement learning modeling is that we can assume what's going on inside of his mind. So what we can observe as a researcher or as an observer, what we can observe is only what he chooses and what he could get as a reward. So this is this is what we can only observe from outside directly, right? But here, the reinforcement learning model assumes what's happening in the unobservable world, the internal mind. And then, so this hidden process would somehow produce the observed data. And then this observed data is then feed back to the hidden process, like learning. And then this again, so we produce the next choice. Then, what we're gonna do is, so then we now have the model. We assume some assumptions about the model. And then we could, using a statistical method, we can infer the parameter values or what kind of model would fit well with this observed data through this model building with statistical estimation method. That's the overview of the reinforcement learning paradigm, right? And then let me then introduce a specific type of the most simplest reinforcement learning model. So this is like first seasons, let's say this is the first season's farmer's belief, preference value, which is called Q value in this talk. So let's assume he has a Q values for each options, wheat and potato. And then for the first season, as I said, he has no preference, specific preference. So the Q values is equal for both options. And then he observed some reward. He experienced some reward at this season. Let's say he obtained some bunch of money from the harvesting these wheat, and then so this reward would update the value of the Q value for wheat, and then so this value update. So the simplest way to do that is, so we assume that these are it's the original Q value and new experience would be averaged by a weighted averaged, right? Then producing the new Q value, so Q value for the next step. And then this weight is called learning rate, or sometimes called step size parameter, or depending on the discipline, I guess. But yeah, this running rate here is taking the value between possibly take 0 and 1, right? So then, so that these two original Q value and reward would be averaged, weighted average. Then this now he has a new updated Q value, right? So preference. We can write down this process using mathematical formula like this. So this is the Q value, original Q value. It'll be weighted summed up, then producing new Q value. So it looks like that. But this formula sometimes also written as like this. When you read some reinforcement learning textbook or some paper, journal articles, so you might often observe the second line formalization, but these are mathematically the same. The second line, there's a red colored term is called reward prediction error. So behavior neuroscientists are looking at this correlation between the brain activity and the reward prediction error, for example. So these are key, but mathematically it's just the same thing. Right, then we have now updated Q value. And then what we need to further model is, so now he has a preference, but somehow we need to model how this value would determine the next choice. So then the next step of the modeling is the function, determining the function of decision making or policy. So now the simplest way to do that is assuming that the Q value would be mapped onto the a choice probability, so that the higher the Q value, the more likely it is that he choose that option, the highest Q value option. And the simplest way, is be using so-called softmax function, or this is a multinomial logistic function actually. So basically it says larger the Q value, so larger the Q, so this is QTA, A is the action, one of the option, and then is averaged by
the sum of these. And why we need exponential, the Q value. So what we want here is the nature that higher the Q value, the more likely that you choose that option, right? But Q value itself could take like a negative word. And for example, if you get some poisoned potato, you get a really negative experience. So then you might be your Q value might be go down below 0, for example. In that case, Q value could negative value, and then without these exponential, for example, then we could just take like a proportion of Q values, but in that case, positive and mix of the positive and negative number would mess up to the probability. So then the simplest way, easiest way is using this exponential so that everything should be positive word. And then there is also often assume so this based on this policy, like a probability distribution of choice, then we assume that the next choice would be generated by like a kind of coin flip or stochastic process based on the choice probability derived. And so as you can see, there's another kind of parameter called beta here. So this beta is often assumed in this type of model, which is sometimes called kind of inverse temperature or something, but which is basically controlling steepness of how would you react or prefer to the most highest Q value option. So basically, the larger the beta value, this functions more further steep. Then the lower the beta value, so this sigmoidal curve is becoming more flat. So that means, and then eventually, so when it's completely flat, then the choice would be just always equally random. So regardless of the Q value, you choose just 50-50 chance you choose potato wheat. But when beta value is approaching to the larger number, you would almost always choose the highest Q value option, even though the Q value difference is only tiny, but you always prefer the slightly tiny higher Q value. So then we can then potentially capture the also individual like behavior strategy, like some cases human or animal may be more explorative, or other cases animals may be more exploitative, the choosing what they believe the best. So these kind of behavior variation could be captured via this beta value. Yeah, now, so in summary, in this basic, very simplistic reinforcement learning model, there are two key parameters. The one is learning rate, as I said, so in a value updating process, and also and then so that beta value, so the inverse temperature, how they are more exploration or exploitation. So to grab the nature of that, let me so this is the kind of like again we do that together in a code notebook. So we have in a website, in a tutorial 2 code notebook, and so there's and so it's not the game as we did yesterday. So this is just each of you can run the simulation on the website. This is called Shiny Up. This is run by somewhere else, and you can run your own simulation. And then what you need to do is just click the run button, and then you can run run of the agent-based simulation of this reinforcement learning model. But you can control the parameters such as the learning rate value or inverse temperature value, as well as how many trials you want to observe, or number of options. So I've only talked about 2-armed bandit in that potato wheat example, but you can of course increase the number of options. So you can observe what kind of how the increasing number of options affect the performance, for example. So yeah, let's try some simulation and think about the question like parameter value, how these parameter values affect the behavior patterns or performance.
Great. So if you're looking for the link, here's the code notebook, tutorial 2, where you can find it under simulating data, demo 1, tweaking individual learning parameters. Okay. And at first you won't see anything until you click the run button. So set the parameters and then click run. And so maybe a good exercise is to see like what type of combination of alpha and beta parameters produce the best learning curves, or just to see how they influence learning curves. And if you're curious to see how the code works, we have a kind of static version of this just above here. And so you can see the code for running the two-learning model. But if you crank the number of options, right, you might kind of think the first option you find is the best one and then kind of never move on from there, right? If it's slightly better than what your initial expectations are. So that can also kind of get you lost in the sense of like getting stuck on a local optima. Because essentially, if you have beta so high, you're not exploring at all. You're doing pure exploitation, right? And so you will need to find a balance, and it's going to depend on the parameters and the environment. We also already have a fixed parameter for the amount of noise in the observations for a specific, when you repeat the same option. So if you play wheat multiple times, sometimes there's variability every different season, right? And so if variability is high, you might learn too strongly some kind of seasonal variability in the observation that could mislead you in future seasons. Maybe we'll move on to the next section now, right? So you guys can also play this a bit more later, but we'll move on to the next section. So if you, as I mentioned previously, there's code here that lets you, that we use to simulate the data. You can take a look at this later. But from that code, we can also create a likelihood function. And we want to use this likelihood function to be able to not only simulate data, but then fit data that we observe and collect from participants. So we can think about a likelihood function, and I realize I added the animation incorrectly here, is that we want to use models to describe experimental data. And this likelihood function describes the probability of the data, D, given some set of parameters that we call theta, okay? So in our case, our Q-learning model is defined by 2 parameters, alpha and beta, that collectively comprise theta. So what this quantity here describes is the probability of getting the sequence of actions that we observe given a set of parameters. And as a very kind of simplest example, I'll talk about a coin flip model. So the coin flip model, the data that we have here is a sequence of heads and tails observations from this coin. And we can model this very simply with the binomial distribution, right? So binomial distribution is designed for modeling coin flips. It has 2 main parameters. This n is the number of coin flips we're trying to model. So, and then this theta is the probability of the heads, right, for the coin. So this is exactly how this model is defined. Here I have 4 different situations that could occur when we flip the coin 10 times. 3 heads, 7 tails, 5 heads, 5 tails, 8 heads, 2 tails, 9 heads, 1 tail. And on the x-axis, this is the theta parameter, probability of heads, okay? And so what we have on the y-axis is the likelihood at different probabilities of heads. So essentially for the different data that we observe, we have a likelihood function that has its highest mass at a different location along the x-axis, right? When we have more heads, we expect the tail, the probability of heads to be higher, and we have a likelihood function to match this. So the likelihood function, as I said, defines probability of the data for a set of parameters, but what are those parameters, right? We don't start with that. And so what we need to typically do is then to estimate this. And this is why it's really helpful to use log likelihoods, which is this new term I want to explain. First of all, since we're modeling multiple data points, not only a single observation, but multiple observations, we need to describe a joint likelihood, right? So to properly write this out, we actually have to have this a product over all each individual observation. Now, this is much simpler using logarithms. And note that we always, by default, use natural logs as opposed to base 10 logarithms in computer science. And this is because when we use logarithms, we can replace this nesting multiplication with a very simple summation, right? In log space, we just have to sum the log of each of these probabilities. And then since these probabilities are always less than 1, no probability is ever larger than 1, that's not possible. The log likelihood for every single probability, so every one of these terms, is always going to be negative, right? So if we're summing over a bunch of negative numbers, we're going to get a negative number out. And thus it's more convenient to express the fit of a model, right, using the negative log likelihood. So we simply invert the sign. And what we get here is going to be a positive number that expresses the amount of error or loss that we get from the model, right? So we assume a specific set of parameters, theta, and then we compute the log likelihood or the negative log likelihood of the data under those parameters. And this captures how much loss there is for those parameters. We want to find a space, a set of parameters where this loss is as small as possible, okay? So smaller values describe better model fits. Now, we can think about likelihoods as a goodness of fit, and a really helpful example is like thinking about casinos, thinking about a game like a roulette. Essentially, we're betting on different outcomes, and the roulette wheel is a good example because we put our money on specific outcomes, and we're essentially putting probability mass on different outcomes. Recall that our reinforcement learning model has stochastic predictions, right? We have a probability of planting wheat, probability of planting potato. Here's the coin flip model. We have a probability of heads, probability of tails. We're essentially betting money or betting probability on different outcomes. This is our likelihood, which can then very simply be computed to the log likelihood. So here are these negative numbers. It's easier to think about it in terms of the negative log likelihoods. Now we have these very simple positive numbers. A smaller number is better. Essentially means that if this outcome happens, I only lose very little. This outcome happens, I lose a lot because we've put more of a bet on heads. Right, so this is the main term that we're working with called log loss. Sometimes for rather abstract mathematical reasons, we sometimes use deviance, which is 2 times this value. So this will also come across sometimes. But in general, we just think about log loss as the main term that we're trying to compute for a set of parameters. Oh, and I mentioned before, if heads comes out, we lose very little, 0.22. If we get tails, we lose a lot more. So we rather want to wisely put our probability mass corresponding to what we think is going to happen, okay? So I mentioned that the code that we use for the model simulations can also be used to very simply tweaked to give us a likelihood function. And so here's a very little tiny bit of pseudocode that that you can use. We actually have the exact Q-learning model likelihood function in the code notebook. But the basic idea is that we have a function here that takes a set of parameters and takes the data as inputs. We start by initializing this negative log likelihood term with at 0, and then we loop through the data. For every observation in the data, we use the model to make predictions. So I've bracketed out a lot here just by saying model parameters to make predictions. And then we have to figure, okay, what was the true outcome that happened, right? And then what we do is we take a negative log of that prediction for the observed action, right? So if you predicted, for instance, 80% chance that the farmer will plant wheat, and wheat was planted, well, we take the negative log of 80%, and we increment our negative log likelihood with that. At the end, we return this value, and that's the negative log likelihood for the entire data. Now, the very simplest way to figure out what these parameters are, theta, is to use maximum likelihood estimation. So this is the simplest way to determine what is the best set of parameters for the data. So here again is a likelihood function. We have different values for theta at the bottom, and on the y-axis we have the likelihood. So let's again use our coin flip model. We have different probability of heads along the bottom, and imagine we have our 8 heads, 2 tails outcome. Here, the likelihood is maximal, largest, at an estimate of theta of 0.8. And so we use this hat on the theta to represent the maximum likelihood estimate. Now, this saying the maximum likelihood is also saying where the negative log likelihood is lowest, right? These are exactly the same concept. And so what we're trying to do is to minimize the negative log likelihood, right? So to minimize the negative log likelihood, to find the theta parameter where that's lowest is equivalent to maximizing the likelihood, okay? And to compute the maximum likelihood, often what we do is we just take this likelihood function described earlier, and we wrap it in some sort of optimization function. We want this optimization function to find the local minima. So in practice, we write a likelihood function. We put this inside an optimization function. There's multiple types of optimization function, gradient descent, simplex methods. or more complex methods like inspired by evolutionary processes. But in general, we had to be careful that often with the models, the loss landscape can have multiple peaks, right? So just like an agent trying to learn can get stuck in a local optima, trying to find a set of parameters that best fits your data, could also have that same problem, where some optimization algorithms may get stuck in different locations in the landscape. There's an exercise you can look at afterwards in the code notebook talking about this issue, where there's a variety of different approaches that you can use to then try to improve the fits of your model. But just be aware that maximum likelihood estimation is the simplest approach. It is also the most prone to potentially mischaracterizing the data, because it might find something that's not truly a good representation of the data, because it gets stuck in the loss landscape. More concretely, here's an example with our simple reinforcement learning model. So let's imagine we have a 3-option problem this time, and along the x-axis we have different rounds of the data, right? So at every single round, we have a series of choices. The black dots correspond to what choices were made by the agent, and the background here corresponds to the choice probabilities of the model given a specific set of parameters, right? So where red represents higher predictions for the model, but sometimes the model is also wrong. It predicted quite high here, but then the agent chose option number 3. So what we do is we take this choice data that we've acquired, right? And then we use this to calculate the likelihood of the RL agent by searching for the parameters to maximize the likelihood. And then this new plot here, it looks quite similar, but actually we've optimized the parameters. And so this is essentially showing the predictions of the model corresponding to actual choices for the parameters that best fit the data. For our Q-learning agents, you guys were just playing around with, we also computed the entire loss landscape for different values of alpha and beta. So we created this agent, we had it play a bunch of rounds, and the square here represents what the true set of parameters are for this agent that we generated. This loss landscape represents the negative log likelihood. So again, in our optimization algorithm, we're trying to search through the space to find the location where it's the lowest. And this X here represents what we got from a maximum likelihood estimation, right? So it's not exactly on the exact set of parameters, but it's also not that far off. But be wary that these contour lines essentially represent areas where we kind of have flat, kind of flatness in the loss landscape. So sometimes the model can't really distinguish so well between different sets of parameters along those spaces, essentially producing very similar predictions. And with some of the math that we described, we've kind of very simplified this in terms of a single specific model. So for a single specific model, we have a space of parameters in which we can explore through. But in the later tutorial this afternoon, we'll also talk about many different models which have different components and different mechanisms. And so for each model, we have its own parameter space as well. So I wanted to clarify that here we're talking about fitting a specific model and finding the right parameters for this one specific model, but we also will have the issue of figuring out which model configuration is correct, and that we'll talk about that later this afternoon.
But now let's assume here's a PR or other conspecifics, also planting or playing the kind of same task in the same environment. So now in this case, now he might be wisely use this observation from the conspecifics or other agent environment. So now that we can think about what type of social influence play a role in this reinforcement learning paradigm. And as Stefano nicely described yesterday, so we can model many different types of social influence in this reinforcement learning framework. But for the beginning, let's start from the kind of basic imitation type of social learning, social influence. So this is in Stefano's talk, this is more or less related to the decision biasing type of social influence. So this means that we only assume the softmax choice probability in a reinforcement learning model, right? But let's assume that this choice, this policy is influenced by social information, such that So frequency dependent copying, this is the term used in social learning literature, cultural evolution literature. So we humans and many other animals tend to have a bias towards copying the popular, copying the option that is chosen by many other people, other individuals. So that means this is like frequency dependent. So the choice probability is impacted by this social frequency information. So this is why. So this is called frequency dependent copying behavior. So then the policy or choice probability of frequency dependent copying to option A is correlated to the frequency information. So the FA is let's say it's a number of other agent choosing option A, right? And then it's a kind of average. But these are theta parameter here, but it's not the same theta in a previous Charlie's short talk. So theta manipulating, controlling the like a sigmoidal curve in a softmax function. So the theta value also controls the strength of conformity bias, how strong it is to follow the majority's behavior, majority's option. So like higher the theta, you are more likely to deterministically follow the most popular option. But the lower the theta, you still follow, more likely to follow the most popular one, but there's also a higher chance that you can also choose not so popular one as well. So, but still there's a positive frequency dependent. All right, then, so let's, for the very beginning, as a simplest, for the simplistic assumption, let's assume that in the population or group, there are two types of learners, right? So one is pure reinforcement learners, without considering any social partners, social information, or social learners or frequency dependent copiers who is whose choice is determined by the frequency dependent policy. So these guys, social learners, are only copying, and then without using their own learning history. So they are always copying others, and then let's see what would happen if these two types of behavior exist in a population. And so then this is the next demo link, and you can control the number of options or a number of total agents right in the population, and you can also control number of social learners within that population. And yeah, you can again control the alpha and beta, but in this case, you can also control the theta value, which is social conformity parameter. So you can see the impact of that. And so the number of trials and the number of replication means the number of simulation you can run, a number of agent, I think, number of replication. Yeah. So yeah, let's try, and you can please let's think about how different ratio of individual social learners would affect behavioral dynamics. And imitation with Rogers paradox. We haven't introduced what Rogers paradox is, but we're gonna come back to that later.
Yeah, I think you get it in the next slide. Right. So then go to demo 2, imitation.
Have you any thought of how social learners, frequency of social learners, how that impact on the behavior, or when social learners better than asocial learners, or vice versa? That's a good point. Yeah, so that makes sense, right? Because here social learners just copying each other. So let's assume if everyone is social learners, then no one actually learned the environment. So just copying each other just randomly. So then in that case, no better behavior would emerge. That makes sense. So generally speaking, the higher the number of social learners in that kind of population, the average performance is reduced. So and actually, so this is kind of called the Rogers paradox. So which is studied by evolutionary anthropology 80s, and so this says so this is a very simplistic assumption. This Rogers model is quite simplistic, but this is kind of similar to the situation what we observed in the demo here. Like the larger the number of social learners, then the population level average decision making accuracy is reduced. On the other hand, when there's purely asocial reinforcement learners population, then the performance is quite good. But there's no then then in that case, so in the population where everyone is asocial learner, then it's good idea to being a copier, because everyone other people are learning, and then you can just join the effort, and they can copy, and then they can have a benefit. But that's true for everyone else. So then the game theoretic point of view, in that case, any other reinforcement learners might be change their strategy, and then they can switch to the social learners, and then gradually population performance is reduced and decrease and decrease, and then evolutionary stable point is stable state would be like where there's no increase. There's the evolutionary stable state. There's switching to either other strategy is not a good idea, so just stick with it. And then this is where on average the same average performance as in a pure reinforcement learners. So there's no benefit of having social learners in the population. And then this was called, why this is called paradox is because this seems to be inconsistent with our intuitive observation or history, like humans should have been benefited by social learning or cultural transmission for this our ecological success. But this is not this theory's prediction. So there's a gap, and then soon after, well, why there's a gap? And this is because model assumption is wrong or inconsistent with the nature. So so this is the original Rogers model, and then this is the huge graph is the simulation of this model. So you can play that in a code notebook. So then that was so then there's a gap between theory and observation, and so then assumption was maybe wrong. So the one key assumption was that social learning is just assumed random, so there's no strategic point of view. So, but normally people or any other animals use social learning more selectively in timing, or or to whom to copy, or the context. So this strategic use of social learning might be key. So then, gradually social learning literature is studying about more strategic way of social information use. Then next we then have to think about so maybe agent can combine the learning and copying, and then together to generate the decision making. So then so this is the a decision biasing influence. So the Stefano talked yesterday. So before we only think about the pure copier. So the social learner always copy others, but we can think about like a combined version of social learners and asocial learners. So let's assume that the choice probability at time t is actually weighted sum of the softmax policy and frequency dependent copying. So weighted by this parameter gamma. So that means this farmer choice depends both on his own belief as well as what others are doing. So this mixed use of learning and copying might be a good idea. So to see what happens if these are more mixed social learning or decision biasing type of social learning, then let's play the next demo 3, and then to see how behavior would be, what kind of behavior would emerge, different type of parameters, especially, changing like a gamma parameter, which is introduced. So, yeah. When you run this type of simulation, I normally do try like a very extreme parameter very fast. Like, for example, trying the theta value equals to 0, for example. In that case, when theta is 0, that means there is no actual social influence, right? Because when theta is 0, when the agent decides to copy something, others, but theta is 0, that means social influence, like you remember the sinusoidal curve when we flatten, so there is no actual social free-case influence. So then when theta is 0, that this combination decision biasing model reduced to the just this, sometimes agents blindly random choosing, and sometimes follows the own belief. This type of behavior. So this type of extreme case will help you to get more idea of what's going on. Yeah. So this is like general tips for the agent-based simulation. So that's the the decision biasing modeling. But yeah, as Stefano yesterday nicely described, we can think about many different types of social influences, right? So we only talked about the choice is biased by social learning, social influence, but like belief updating might also biased by how popular each option is, and also we can also think about more advanced, more complex metacognition, or more about how they update or how they assume the other agent behavior is also influence the foreground agent behavior. So yeah, now so Charlie will be talking about like these different types of social learning strategies would generate the different types of social learning patterns. Yeah, so then we can then focus on the value shaping type of social influence. So the value shaping, so as I said, so this other agent could now impact on the belief states of the focal farmer, right? So such that this now Q value of option A is biased by the how popular this option A. So directly into the value state. And then, yeah, now, so rather than simulating this value shaping population, but now the next demo, you can run the mixed population. So that is a 4-agent group, and you can change each agent behavior strategies and each associated parameters. So you can run, of course, the 4 pure value shaping learning group, but also you can try 2 value shapers and 2 decision biasing guys, or 2 value shaper and 2 pure reinforcement learners. So you can change the component of the group, and you can, yeah. So there are a bunch of things you can change. So yeah, you don't have to entire exploration today yet, but here, but you can do that later in your place after one. But yeah, let's try what happened when you choose the value shaping rather than decision biasing. And if you have any thoughts, or yeah, the simulation is very interesting stuff. I know, so you can play it. You should continue it as well. But yeah, let's you can come back any questions or thoughts later on. But yeah, let's move on to the next.
So maybe one really quick thing, like value shaping is one of the most simplistic approaches to use social observations to inform our values about the world, right? But we can also think about more complex methods where we really unpack their actions, their behaviors, and try to apply it to our own setting. And we can think about this in terms of theory of mind. So theory of mind is the ability that humans, all humans have but it's something much more debated in terms of animals. But this aspect of human of social learning that's is really powerful, so we can unpack observed actions into imputed mental states, right? So for instance, we can observe some actions that people have taken and infer what value representations they have for different options. Seeing which snacks people pick, maybe inform me about which values they have for what types of food preferences they have. It might also infer something about their beliefs about the world, about the structure of the world. Maybe someone is grabbing a bunch of food now because they know that there's not really time later. And you can also tell something about their intrinsic rewards about the world. Right? So we think about value as kind of instrumental value in terms of how we select actions, but we may also learn something about their individual preferences. They prefer broccoli or they don't like cheese, for instance. And so theory of mind is this process that we take these actions and then unpack it. And then having unpacked it into value or beliefs, we can then use that to inform our actions, our own values, or our own beliefs about the world. Or as Stefano was talking about yesterday, can also impact our own reward preferences. Maybe seeing some people eat healthy food a lot makes me also want to eat healthier and eat more vegetables. The first type of kind of theory of mind strategy I want to talk about is value inference. And we can think about this as something that's a bit more flexible than this direct imitation of behavior, which we get through value shaping. So the basic idea is that we observe someone else's actions and we then infer something about their value, their values about the world, and then use that to inform our own values this way. So value shaping is kind of going directly from action to value. Here we're first inferring the value and then using that to inform our own. And one framework for performing this type of inference is to use inverse reinforcement learning. And so the basic idea follows Bayes' rule, where we're trying to infer some distribution over values given their action. And this is proportional to some prior beliefs about their value and a likelihood, right? So for any specific value function that we might have about the world, we can generate predictions about actions via some sort of policy, okay? But as you probably know, this is intractable because there's an infinite possible number of value functions that we have in the world. And then for each, we can't simply do this type of, we can't really compute this analytically. So unfortunately, it's intractable for most interesting problems. But as a normative framework, it's also been very helpful for discovering inductive biases that kind of point a bit towards how humans might do this. And one inductive bias is known as the principle of efficient action, where we essentially assume that this is going to be maximizing value as much as possible, right? There's a lot of possible actions you can take based on your value function, but if you assume that you're only going to select actions that maximize your value, then this kind of constrains the problem a bit. We still have the problem of there's an infinite number of value functions, but in some ways we can still constrain this a bit. And this type of constraint is also reflected in how humans perform this type of inference as well. Even from children at a young age, assume that people select value maximizing actions, that we expect people to behave in this way. And so this is kind of points a bit towards how humans might do this, but it's still a very difficult computational problem. There are sample-based approximations. We'll talk a bit about sample-based methods in tutorial 3 later this afternoon in terms of Bayesian methods. But we still are looking for cognitively plausible methods for doing this type of inference. Now, in what way would this type of inference be more flexible than directly imitating actions? Well, for instance, imagine you see someone ordering a really nice pizza at a restaurant, right? And you also want to order the same pizza. So value shaping lets you do that, right? You assign value to that exact pizza. However, perhaps the menu has changed. Perhaps that item is no longer available, or maybe there's some other specials. With value shaping, with this kind of value inference, we infer something about that pizza having high value, but then we can also apply this to new choice sets, right? And to new settings. We can also modify it based on different contexts. And so this, in this sense, inferring that their value and then applying this to new settings offers a bit more flexibility. We can also go even a bit higher up this decision-making hierarchy by performing model-based inferences, right? So not only inferring their value, but inferring something about their beliefs about the structure of rewards, right? So we can kind of unpack this a bit further when we've broken down value into 2 different components of what beliefs, B, and rewards are where beliefs represent something about the causal structure in the environment, right? We think about beliefs as being, oh, she thinks local markets have fresher produce, right? Because we see somebody carrying some groceries from a local market and they look really nice. And we might infer something about the structure of the world based on the fact that a local has visited the market. And then rewards here represent something about the intrinsic specifications of that individual. That individual has their own reward preferences, right? And if you combine these beliefs and rewards together, we get something that represents the value that person has. And then from value, we can then get to actions by forming a policy. Now, this type of model-based inference is more complex than value inference because often we have to go through value to infer beliefs and rewards. And in addition, we also have evidence from developmental psychology that suggests that there's also this hierarchy in terms of development. In the first, children as young as 1 year old are already in this teleological stage of representation. So they can represent goals of the other people, where goals are just another way to say values. And so children as young as 1 can represent goals of other people, whereas mentalistic representations, this outer ring of the circle, comes online much later to represent different beliefs that people have. Beliefs are different from one's own. And so this type of model-based inference is the most flexible in terms of how we can apply this to our own settings. Seeing people perform behaviors that maybe are not relevant for us could still inform us how to behave. For instance, if you see someone running for the bus, maybe we're not trying to catch the same bus, but it can inform us something about how we should also behave in the world because we learn something about the structure. And this allows us to kind of have maximal flexibility in applying it to our own context, based on our own goals, based on our own settings, and based on our own abilities as well. Right? Sometimes we observe people, professional athletes, doing things that we should definitely not imitate directly, but we can nevertheless learn something about. So we're going to wrap this tutorial today with some summary and open challenges. So we've shown that social learning deploys a wide range of tools, and we've shown you some of the simplest tools in this toolbox with code also in the notebooks. We've looked at imitation, direct copying of observed behavior. We've talked about value shaping, which adds a heuristic bonus to the value representations of the behaviors we observed. But we can also go a bit higher up and do some unpacking of mental states via theory of mind. We can infer hidden value representations that people have. We can infer beliefs, hidden beliefs about the world. However, this is still only a subset of the possible social learning mechanisms that humans and animals have access to. Intelligent behavior is not only a function of each individual, but also how well groups collectively solve behavior, right? We've seen this with Ian's talk and through Ari's talk. It's not only these individual behaviors, but also how we form these connections and how we collectively solve, coordinate to solve problems. And these models here have only really looked at kind of small timescales of learning. But another important aspect about human social learning and also just social learning in general is over large timescales, right? Really long timescales where simple innovations can cumulatively add up to produce massive cultural solutions, massively complex cultural solutions, like the evolution of computers or hammers from Eleanor's talk yesterday. And as well, we've so far only really focused on observational learning here, right? Observing behaviors, but so much more of social learning involves pedagogy and explicit communication. I think Mark will talk a bit, Mark and Natalia will talk about that during later sessions. But I think the important thing is that for any of these mechanisms that we can describe verbally, we can also define a computational model that makes precise commitments to different mechanisms of behavior. After lunch, we'll have tutorial 3, where we'll show you how we can test these hypotheses about different mechanisms of behavior against one another, and through data, resolve what are the right and the most plausible mechanisms, and then interpret behavior via that lens of computational modeling.